Hello, this is number 10 on the practice final. It deals with the Z transform. We're told we have an interconnection of discrete time LTI systems. We've been given H1 of n and H2 of n. We're asked to find in part A the Z transform H1 of Z and H2 of Z, and to specify their regions of convergence. So we will start with h1 of z, so h1 of n is given, it's delta n minus 1 minus delta n minus 2. We can go to our table of z transforms. We know that delta n maps to 1, and we know also that we see two time shifts here. So in the z transform, the time shift alters the transform like so. We get z to the minus n naught times the regular transform had it not been shifted. So we can apply this directly. So we get h1 of z is equal to the time shift here is 1. The transform is just 1, so we get z to the minus 1 since n naught is 1 minus, same deal here, transform of delta n is 1. The time shift here is n naught equals minus 2, so we get z to the minus 2. It asks us to specify the region of convergence. We could write this like 1 over z minus 1 over z squared. You can see here pretty clearly that there's two poles in this function, one at 0 and two more at 0. So this third order pole at z equals 0. So the region of convergence for h1 of z is going to be all of z except the pole which is 0. Okay, so let's find h2 of z. We've given h2 of n. It's equal to 1/2 n minus 1 u of n plus 2. So as usual, we can go look at the table to find the z transform. However, before we do that, we see a time shift. In each case, however, the time shift is not uniform across the function. This part and this part are being shifted differently, so we want to take care of that. So we can write h2 of n. This is just a neat little algebra trick I'm going to do. We can write 1/2 n minus 1, and just like we can multiply by 1, we can also add 1 if we also subtract 1, and that holds true actually for any number. We can add a if we subtract a, so we need to get a plus 2, so minus 1 plus 3 is 2, so plus 3 minus 3 u of n plus 2. We know our properties of exponents. We can separate this off, and we can write 1/2 n minus 1 plus 3 is n plus 2. Now we have this negative 3 left. We can separate that off, so we get 1/2 to the minus third power un plus 2. We can further simplify this. h2 of n equals 1/2 n plus 2. We're going to bring this out to the front. 1/2 raised to the negative third power is going to be 2 to the third power. That's 8 times u of n plus 2. We now have a uniform time shift in our entire function. We can go look at the table of z transforms. This z transform is known. It's going to map to this going to be alpha n times u of n Okay, so the region of convergence for that, we can grab it off the table or you can just see it. It'll be everything but the pole. The pole is alpha. So here we have alpha as equal to 1/2. We also have a time shift, so we know how the time shift acts. It's gonna multiply it by the z to the minus n naught factor, and then we can write it like this. h2 of z is equal to 8 times z minus 2, that's the time shift. Z minus minus 2 is plus 2. 1 minus 1/2, that's the alpha. Z minus 1. The region of convergence for this is all of z greater than 1/2. Okay, so let's move on to C. It asks us to find the total transfer function, and just before, just to be clear, I said that the h2 of z converged for all but alpha, but it converges for all greater than alpha, so that's a distinction there. I need to be careful. H of z will be equal to h1 of z times h2 of z. Sorry, there are very loud birds outside my window. I think you can probably hear them. So we have z to the minus 1 minus z to the minus 2 times h2, that's 8z squared, 1 minus 1/2 z to the minus 1. We can simplify this. We get z to the minus 1 times this, we'll get 8z 1 minus 1/2 z to the minus 1 minus 8z to the minus 2 times z squared is just going to be 1, so that cancels. This will equal 8z minus 1 minus 1/2 z to the minus 1. We've also been asked to find the domain of the functions. So this is h of z. Here we know that we can simplify this a little further. So if we multiply by c over z, we'll get 8z times z minus 1 divided by z minus 1/2. And now we can choose the zeros. The zeros of the function are the values that make the function 0, so these will be selected from the numerator term in a rational number. So z equals 0 is a 0, z equals 1 is a 0. The poles of the function are the values of 0 that make the function undefined. So these will be the values of the denominator that these will be the zeros of the denominator, because if you have a 0 in the denominator, you'll have the function undefined. So the poles of a function are the zeros of the denominator. So we can pick it out by inspection. Z equals 1/2. It wants us to draw this domain, so we have a pole here, 1/2, the region of convergence from earlier is just going to be z greater than 1/2, so this is 1/2, this is a pole. So we want to map this in. We can also see that this function would be undefined for z equals to infinity, because we have a second order polynomial in the